Hi, in this video, I will be showing you problem number 31 of chapter 14, section 6. The temperature T in a metal ball is inversely proportional to the distance from the center of the ball, which we take to be the origin. The temperature at the point 1, 2, 2 is 120 degrees. A. Find the rate of change of T at 1, 2, 2 in the direction toward the point 2, 1, 3. B. Show that at any point in the ball, the direction of greatest increase in temperature is given by a vector that points towards the origin. So, the information given in the problem are the temperature of the ball, and it's inversely proportional to the distance from the center of the ball, and the temperature at the point 1 to 2 is given, which is 120. Then in the first part it is asking us to find the rate of change of T at 1 to 2 in the direction towards 2, 1, 3, which is kind of finding directional derivative. And then the second part is asking to show that at any point the direction of greatest increase in temperature is given by the vector that points towards the origin. So let's start off with the first information given in the problem. It's about inverse proportionality of the temperature at any point and the distance of the point from the center of the ball. So it's given that temperature at any point P with coordinates x, y, z on the ball is inversely proportional to the distance of the point from the origin. It's inversely proportional. So we can write T of x, y, z, or temperature at any point at x, y, z as k divided by square root of x square plus y square plus z square. Because it's inversely proportional, then the constant of variation goes on the numerator. The denominator is distance of the point from the origin. So the distance of the point from the origin is square root of x square plus y square plus z square. So that is what the denominator is here. So now the distance is OP, which is square root of x square plus y square plus z square. That goes in the denominator. So we'll call that expression as 1. We have to find out what this k is. We are given some information to find out k. The temperature at the point 1 to 2 is given, which is equal to 120. So T at 1 to 2 is given to be equal to 120. We will use that information in equation 1. So we'll substitute 1 to 2 into the first for x, y, z, and then equate that to 120, and we'll find out what k is. So using 2 into 1, we get 120 equal to k divided by square root of 1 square plus 2 square plus 2 square. That will give us the value of k equal to 120 times square root of 9, which is 3. So that will be 360 for the value of k. So we can get this back into the original expression for t. We can replace the value of k by 360 in 1. So T of xyz now becomes 360 divided by square root of x square plus y square plus z square. So this is the function, this is the temperature function now. The numerator here is 360. Next part A, find the rate of change of T at 1, 2, 2 in the direction towards 2, 1, 3. In the direction 2, 1, 3, which is finding the directional derivative in the direction towards the point 213. This is to find the directional derivative du t, where u is the unit vector in the direction of p to q, where p is 1, 2, 2, q is 2, 1, 3. In the direction of the vector joining the point 1, 2, 2 to 2, 1, 3. So we have seen several problems earlier to find the directional derivative. In order to find out the directional derivative, we need del t. So the gradient vector dot product with the unit vector u in the direction of in the direction vector is what we have to find out in order to find out the directional derivative. So t at xyz, I will take from the previous slide, which is 360 divided by square root of x square plus y square plus z square. That is 360 times x square plus y square plus z square to the power -1/2. So it's easy for us to differentiate if we keep the expression like this. Then nebula t or del t, which is the gradient vector of t at xyz, which has components t sub x, t sub y, t sub z, which are partial derivatives of t, with respect to x, y, and z are the components, which is 360 times -1/2 times x square plus y square plus z square to the power -1/2, -1, which is -3/2, then times inner derivative, which is 2x. That is the x component. Similarly, we can write down the y component and the z component. So everything will be the same except here 2x. There it will be 2y, the next component, and this z component will be everything is the same except 2x or 2y, that will be 2z. So that will be our gradient vector. So you notice that here 360 times, then here you have 2 and 1/2. So these two will get cancelled out. So we will have negative of 360 times which is negative of 360 times x square plus y square plus z square to the power -3/2, which can be taken out as a common factor. Then it will be x, y, z. So this is our gradient vector at t. Then gradient vector of t, temperature function. Then gradient vector at 1, 2, 2 at this point is obtained by plugging in x equal to 1, y equal to 2, and z equal to 2. So it is -360 times 1 plus 4 to the power -3/2 times vector component 1, 2, 2. That is the gradient vector at the point 1, 2, 2 for the temperature function. So which is -360 over 27 vector 1, 2, 2, because this expression here is 9 to the power -3/2. That will be 3 squared to the power 3/2. So that will be 3 cubed. That is 27. That's how you get 27 in the denominator. Further simplifying, we get -40 over 3, 1, 2, 2. So this gives the gradient vector at this point, at the point 1, 2, 2. Then the unit vector in the direction of the line join of 1, 2, 2 to 2, 1, 3. So we have to take the vector join of these two and then divide by the length of the vector. That's how we make it unit vector. So unit vector is a vector of length 1. So we get 2 minus 1, 1 minus 2, 3 minus 2. We are subtracting the components of the first from the second. Then we take in the denominator the length of the vector So it is 1 square plus negative 1 square plus 1 square. So it's 1 negative 1 1 divided by square root of 3. So now, in order to get the directional derivative, we are going to only dot product delta t, del t, which is the gradient vector, with this unit vector. So which is negative 40 over 3, 122 times 1 over radical 3, 1 negative 1 1 vector components in the vector component form. So if we multiply the corresponding components and add, we get negative 40 over 3 radical 3, and then if you dot product these two vectors, it's going to give 1. So it is negative 40 over 3 radical 3, which is the directional derivative of t in the direction of u, in the direction of the vector, unit vector u. Now, there is a second part to this problem. It says that show that the direction of greatest increase in the temperature is given by a vector that points towards the origin. Direction of the greatest increase in the temperature points towards the origin. So the greatest increase always is taking the gradient vector always points in the direction of the greatest increase. We saw that in the previous problem too. And then in this case, we are going to find out that vector and analyze it, and then say that it points towards the origin. So from part A, del t, which is the nebula t or the gradient vector t at xyz, is negative 300 times x square plus y square plus z square to the power negative 3 halves times the vector xyz in the component form. So what is the concept that we are using here? If A is a vector with components A, B, C, then opposite of A, the negative A will have components negative A, negative B, negative C. So this points exactly in the opposite direction of the original vector A. So if you consider xyz to be the position vector of the point P, the original point P with coordinates xyz is OP, and it has components xyz. And if you look at this del t, a nebula t, or the gradient vector t, it is negative of a square expression times xyz, which means it is obviously pointing towards the origin. One is away from the origin, the position vector. The other one is pointing towards the origin. Here, the position vector of the point P is OP, which is vector components xyz. As del t, the gradient vector, is negative of xyz times 300 over x square plus y square plus z square to the power 3 halves. Obviously, this points towards the origin. So, vector del t points towards the origin. In fact, the vector OP and vector del t are in the opposite directions. Note here, del t points in the direction of the greatest increase of the temperature. Hope this video helps.